This situation involves a residential electrical system with an unusually long run of number 14 wire powering 3 bulb post lights, totaling approximately 590 feet. The primary concern is significant voltage drop due to the undersized wire and the extended distance. The initial question proposes using 2 boost transformers to compensate for the voltage drop, potentially avoiding the need to replace the existing wiring. However, installing boost transformers may not be the most effective or safest solution for several reasons. Firstly, there is excessive voltage drop. With a total run of 590 feet using number 14 wire, the voltage drop at the end of the circuit is likely significant, exceeding the allowable 5% limit specified by the National Electrical Code. Boost transformers can only increase the voltage within a limited range, and 2 transformers might not provide enough boost to overcome the substantial voltage drop in this case. Secondly, there is the risk of heat generation. Overloaded wires, especially those experiencing significant voltage drop, can generate excessive heat, posing a potential fire hazard. Installing boost transformers adds an additional load to the circuit, which could further increase heat generation and exacerbate the risk of overheating. Thirdly, there is the issue of incorrect wiring. Given that the original wiring was done by an unqualified individual, there are legitimate concerns about the overall safety and reliability of the installation. Adding boost transformers to an incorrectly wired circuit may introduce further complications and potential safety hazards. Instead of relying on boost transformers, there are better solutions that prioritize safety and effectiveness. One option is to pull a new circuit. This is often the most reliable and safest approach. It involves running a completely new circuit with appropriately sized wire to meet the load demands of the post lights. Selecting the correct wire gauge will minimize voltage drop and ensure safe operation. Another option is to increase the wire size. If pulling a new circuit is not feasible due to logistical or cost constraints, consider replacing the existing number 14 wire with a larger gauge wire, such as number 12 or number 10. Using a larger wire size will reduce the voltage drop and improve the overall safety and efficiency of the circuit. To accurately determine the appropriate wire size, several factors need to be considered. These include the total load in amps, the length of the circuit run in feet, and the allowable voltage drop, which is typically 3% for branch circuits feeding lighting loads according to the National Electrical Code. Using these values, voltage drop can be calculated using the following formula. Voltage drop equals 2 times the length of the wire in feet times the current in amps times the constant K divided by the circular mils of the wire. The constant K represents the direct current resistance for 1 circular millifoot of copper conductor. For copper, the constant K is typically around 12.9 ohms at 20 degrees Celsius. The circular mils represents a unit of area used to describe the cross-sectional size of a wire. Larger circular mil values indicate thicker wires with lower resistance. The National Electrical Code Article 210.19a dictates that branch circuit conductors shall have an ampacity not less than the maximum load to be served. This means the selected wire size must be capable of handling the total current drawn by the post lights without overheating. Table 310.15b16 in the National Electrical Code provides ampacity ratings for various wire sizes based on their insulation type and installation conditions. The table lists the allowable ampacities for conductors based on insulation type, such as THHN, THHW, and XHHW, and installation conditions, such as whether the conductors are installed in raceways, cables, or free air. The values in the table assume that the ambient temperature does not exceed 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher, correction factors must be applied to reduce the allowable ampacity. For example, if the total load of the post lights is 15 amps and the circuit will be wired with THHN copper conductors installed in conduit, then according to the National Electrical Code Table 310.15b16, The number 14 AWG conductor with a 90 degrees Celsius insulation rating has an ampacity of 25 amps. A number 12 AWG conductor with a 90 degrees Celsius insulation rating has an ampacity of 30 amps, and a number 10 AWG conductor with a 90 degrees Celsius insulation rating has an ampacity of 35 amps. Given the 15 amp load requirement, a number 14 AWG conductor would appear to be adequate from an ampacity standpoint. However, the voltage drop calculation will likely necessitate a larger wire size. The National Electrical Code Section 215.2 (AONA) recommends that feeder conductors be sized such that the voltage drop does not exceed 3% for lighting, heating, and power loads, or a maximum of 5% for the combination of feeder and branch circuit. For sensitive electronic equipment, a low voltage drop may be necessary to ensure proper operation. To minimize voltage drop, increase the conductor size and shorten the circuit length. For a 120 volt circuit, a 3% voltage drop would be 3.6 volts, and a 5% voltage drop would be 6 volts. Using the voltage drop formula, the actual voltage drop can be calculated for various wire sizes to determine the most suitable option. For example, consider a 590-foot run of number 14 copper wire carrying 15 amps on a 120-volt circuit. The circular mils for number 14 copper wire is 2082. The voltage drop would be calculated as follows. Voltage drop equals 2 times 590 feet times 15 amps times 12.9 ohms divided by 2082 circular mils, which equals approximately 11.4 volts. This represents a voltage drop of 9.2%, which exceeds the recommended 3% limit for lighting circuits. Now, consider using number 12 copper wire instead. Number 12 copper wire has a circular mil area of 6,530. The voltage drop would be 2 times 590 times 15 times 12.9 divided by 6,530, which equals approximately 3.5 volts. This voltage drop is 2.9%, which is within the recommended 3% limit. Next, consider using number 10 copper wire. Number 10 copper wire has a circular mil area of 10,380. The voltage drop calculation is 2 times 590 times 15 times 12.9 divided by 10,380, which equals 2.2 volts. This is equal to approximately 1.8% voltage drop, which is well within the recommended limits. Based on these calculations, number 12 AWG copper wire would likely be sufficient to meet the voltage drop requirements for this circuit, while number 10 AWG wire provides an even lower voltage drop margin. Another consideration is the type of insulation used on the conductors. THHN and DHHW are common insulation types for building wire, and they have different temperature ratings. THHN is rated for 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations, while THHW is rated for 75 degrees Celsius in both dry and wet locations. When selecting the appropriate wire size, it is essential to consult the National Electrical Code tables and consider any applicable directing factors for ambient temperature, conduit fill, and other conditions. Directing factors are used to reduce the allowable ampacity of conductors when they are installed in conditions that limit their ability to dissipate heat. For example, if multiple current-carrying conductors are installed in the same conduit, the ampacity of each conductor must be derated to account for the increased heat generated by the group of conductors. The National Electrical Code Table 310.15 provides adjustment factors for more than 3 current-carrying conductors in a raceway or cable. Similarly, if the ambient temperature exceeds 30 degrees Celsius, the ampacity of the conductors must be derated using correction factors provided in the National Electrical Code Table 310.15 B2A. Voltage drop can also be reduced by using parallel conductors, which involves running 2 or more conductors in parallel for each phase and neutral of the circuit. This effectively increases the overall ampacity of the circuit and reduces the voltage drop. The National Electrical Code Section 310.10H provides requirements for the use of conductors in parallel. The size of the overcurrent protection device, such as a circuit breaker or fuse, must also be considered when selecting the wire size. The overcurrent protection device is designed to protect the circuit from overloads and short circuits, and its ampacity rating must be matched to the ampacity of the smallest conductor in the circuit. The National Electrical Code Section 240.4b provides rules for the protection of conductors against overcurrent. Finally, it is highly recommended to engage a qualified electrician to assess the specific situation and recommend the best solution. A qualified electrician has the knowledge, skills, and experience to properly evaluate the electrical system, perform the necessary calculations, and ensure that the installation complies with all applicable codes and standards. In conclusion, while installing boost transformers might seem like a quick and easy fix, it is generally not a safe or reliable solution for addressing excessive voltage drop in a long lighting circuit. Opting for one of the suggested alternatives, such as pulling a new circuit or increasing the wire size, will ensure the safety and proper functioning of the post lights while adhering to the National Electrical Code requirements. It is important to prioritize safety and consult with a qualified electrician to determine the most appropriate and code-compliant solution for the specific electrical installation. Addressing voltage drop effectively not only improves the performance and longevity of electrical equipment, but it also reduces the risk of electrical fires and other safety hazards. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician for any electrical work or modifications to your home or business. Neglecting electrical safety can have serious consequences, including property damage, injury, and even loss of life. Adhering to the National Electrical Code and employing qualified professionals is essential for ensuring the safe and reliable operation of electrical systems. When choosing an electrician, verify their credentials and experience, and make sure they are licensed and insured. A reputable electrician will be able to provide references and demonstrate a commitment to safety and quality workmanship. By taking these precautions, you can help protect your home or business from electrical hazards and ensure that your electrical system meets all applicable codes and standards. The correct sizing of electrical conductors is an essential aspect of electrical system design and installation. Proper conductor sizing ensures that the conductors can safely carry the intended load current without overheating or causing excessive voltage drop. Undersized conductors can lead to a number of problems, including reduced equipment performance, increased energy consumption, and a higher risk of electrical fires. In addition to ampacity and voltage drop, other factors to consider when selecting conductors include the type of insulation, the ambient temperature, and the presence of corrosive substances. The type of insulation must be suitable for the intended application and environment, and the ambient temperature must be taken into account when determining the conductor's ampacity rating. Conductors that are exposed to corrosive substances may require special insulation or protection to prevent damage. The National Electrical Code provides detailed requirements for conductor sizing and installation, and it is important to follow these requirements carefully to ensure a safe and reliable electrical system. The National Electrical Code is updated every 3 years, so it is important to stay current with the latest edition. In addition to the National Electrical Code, local electrical codes and regulations may also apply. These local codes may be more stringent than the National Electrical Code, and it is important to be aware of them and comply with them. Working with electricity can be dangerous, and it is always best to hire a qualified electrician to perform any electrical work. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and in accordance with all applicable codes and regulations. Attempting to perform electrical work yourself without the proper training and experience can be hazardous and may result in serious injury or even death. If you are not comfortable working with electricity, do not hesitate to call a qualified electrician. Your safety and the safety of others depend on it.